In previous lecture, we already diagonalized the Hyperfine Hamiltonian, and from now on, we will talk about the coupling between spin and atomic orbital angular momentum. Here, the coupled basis between spin and atom. And because we already know that there are spin angular momentum, the spin angular momentum and of the electron, and as well as atom isospin. So total angular momentum of hydrogen atom and we call it as F. Hyperfine structure angular momentum F is that addition between the electronic spin plus isospin. Here we do not consider for orbital angular momentum, but only consider spin angular momentum. Spin angular momentum. We already discussed for the orbital angular momentum in the previous lecture in undergraduate course. Here in ground state, and the L equal to 0 case, and the here we should define that the commutation relations of the total angular momentum of a hydrogen atom Fx and Fy. Then it is that Sx plus Ix and Sy plus Iy. Then this commutation can be calculated Sx and Sy plus Sx and Iy plus Ix and Sy and plus Ix Iy, the commutation relation. And because in this spin and isospin, it should be 0. And also here it is IH bar Sx and plus IH bar IG, not X but G. So it is IH bar FG. So this total angular momentum is well defined by the conventional angular momentum commutation relation. So and here let the F and MF is the eigenstates of coupled basis eigenstate of F square and Fg in coupled basis. Then let's think about that matrix of Fg. And because Fg is the summation Sg plus Ig, so it is 1/2 H bar, and the spin is that here it is 1 minus 1 minus 1, and we already discussed for that, and the spin plus plus and plus minus and minus plus and minus minus. So it is a minus in the electronic spin, it is minus, eigenvalue is minus. So R1 is all 0 case, and plus isospin h bar. In this case, 1 minus 1, 1 minus 1, and the off diagonal is 0, because here in this case plus plus and plus minus and minus plus and minus minus here in this case, and the atomic spin plus minus plus and minus, so plus minus plus minus. Then the addition of the SG and plus IG is that H bar and it is a 1 0 0 minus 1, because our other terms are 0 like this, and here we can think that here it is this Hamiltonian subspace, this matrix subspace, it is degenerated. Here it is, we can define that it is a degenerated subspace. So we should diagonalize this matrix. Then here MS and MI eigenstate of Fg. So, and when we apply this Fg to the MS and Mi, then it is Sg plus Si and MS Mi. So it is that MS plus Mi H bar MS Mi. So this total angular momentum operator behaves like a conventional angular momentum operator. So, and the Fg applied to the MF, it is a eigenstate of the capital F. So in this case, capital MF H bar F MF, like here MF is that MS plus MI, and it is MS is that the spin 1/2 plus minus spin 1/2 and plus minus spin 1/2. So there are 4 possibilities. One is that the 1 0 0 minus 1. So it is a diagonal component. It is a diagonal component of Fg. So we already calculated for the Fg matrix here, and it is a diagonal term 1 0 0 minus 1 is like 1 0 0 minus 1. It is a combination between the electronic spin and the isospin. So secondly, let's consider for the matrix of F square. Then F square means that S plus I square, then is S square plus I square plus 2 times S dot I. So we already know that S square MS MI is that 1/2 and 3/2 H bar square MS MI, then 3/4 H bar square MS MI. Likewise, I square to the MS MI is that 3/4 H bar square MS MI. So the matrix elements of the F square is that here S square matrix. In previous lecture we calculated for the S square matrix, and in the previous lecture we already calculated S square, and example S square. S square is that S square plus I square. S square plus I square is that two same with each other. So 3/4 h bar square times 2, and the matrix element is that the 1 1 1 1, because here plus plus and plus minus and minus plus and minus minus always same eigenvalue, like irrespective of ms and mi, the eigenvalue also identical, so it is 1 1 1 1. And otherwise is 0. And secondly, there should have the two times s dot I. In the s dot I, we already know that s dot I have the, in previous lecture there is s dot I matrix elements is that here 2 times, and it is 4, and 1 minus 1 2 2 minus 1 1, and the other terms are all 0, like this. It is this one is the matrix elements of the s dot I, what we calculated last lecture. So it is, we should know that it is undiagonalized, so it should be diagonalized. Then the addition of these two terms have this h bar square, and here 2 1 1 1 1 2, and 0 0 0 0 0 0 0, like this. It is also degenerated Hamiltonian. Degenerated Hamiltonian should be diagonalized. So then we should diagonalize this. We should diagonalize this term, this subspace. It is 1 minus lambda 1 minus lambda 1 1, and it is 1 minus lambda square minus 1 equal to 0. Then 1 minus lambda equal to plus minus 1. Then lambda equal to 0 or 2. And also we know that the f square to the f mf is that f plus 1 h bar square f mf. So, and in the first case, the lambda equal to 0 case, and here, and f equal to 0. In the second case, lambda equal to 2 case, and here the subspace, and 0 1 1 0 c1 c2, so it is a 0 case. And also here 2 case, it is minus 1 1 1 minus 1 c1 c2, equal to 0, so it is a C1 or C2 we call with each other. And also here in the F equal to 1 case, because here we can think that here when we substitute here, and it is f square f mf is that 2 h bar square f mf. That is corresponding to the this lambda equal 2 case. So it is lambda, it is 2 that is satisfied. So this FMF has the state 1 or 0 case, 1 or 0 case. In both cases, and also in both cases, MF equal to 0, MF equal to 0 case. So, and here, and there are two possibilities, 1 0 or the 0 0 case. And in the 1 0 case, and here 1 over square root 2 and plus minus plus minus plus, it is couple the state, and also in 0 0 case, and 1 over square root 2 plus minus 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 plus. So when you think that it is coupled basis, it is coupled basis because it represented for the total angular momentum, and it is uncoupled basis because they represent by the linear combination of the two eigenstates. So then we can make that here 1 1 is that spin up, and the 1 0 is that 1 over square root 2 and plus minus plus minus plus, and as 1 minus 1 case is that minus minus case, and 0 0 case is that 1 square root 2 and plus minus and minus minus plus. So these three states, this f equal to 1 case, and this one is the f equal to 0 case. So it is triplet state, and it is a singlet state. Therefore, we can find that this total angular momentum and their basic basis like this. So let's go back to the hyperfine Hamiltonian. Because we already know that the hyperfine Hamiltonian is that A over h bar square and s dot I. Because f square is that the s square plus I square plus 2s dot I. So S dot I means that here A over 2h bar square and f square minus s square minus I square. Here, because f square and s square and I square, there is they represented by representative by matrix elements. So this Hamiltonian can be written down as the for example, therefore we should calculate the matrix elements of the f square, s square, and I square. But we already know that s square and I square matrix elements. So let's think that the f state because we already know that f square and f and mf is that f plus 1 h bar square f mf. So and the matrix element, let's think about that matrix elements of the f square. Let's think that matrix elements of the f and mf. Here 1 1 1 0 1 minus 1 and 0 0. There are four possible state. One is this is a triplet state. It is a triplet state and it is a singlet state. So 1 1 1 0 1 minus 1 and 0 0 state. And also because from this relation, when you apply the f square here and the f square in the one case, when you apply here, it is a 1 times 2, so it is a 2, and also here it is this term is 0, so it is 0. Other things are because of the orthogonality and all 0 case. So it is f square matrix can be written down like this. So hyperfine put over the Hamiltonian is that h bar square can be cancelled with each other. So a half it is a 2 0, and other things are all 0. And also secondly, minus a half and the s square is that s square f mf is that 3/4. So it can be written down as the 3/4 and 1 1 1 1, and all other terms are 0. Also I square also same with each other. So I square same with like this. So it should be times 2. So when you calculate here, then it is a to the 4th and 1 1, 1, minus 3, and off diagonal term is 0. So it is a 1, 1 state and a 1, 0 state, 1, minus 1 state, and a 0, 0 state. So it is the triplet degenerated triplet state. F equal to 1, and it is a single state. F equal to 0 case. So there are two energies. In the first hyperfine perturbed energies, first perturbed energy, there are two energies. One is that A fourth, and the other one minus 3A fourth. And here F equal to 1 case and equal to F equal to 0 case. So it is the same with the hyperfine Hamiltonian eigenvalue problem in previous lecture.